Well, welcome everybody. It's wonderful to see everybody here today. And I'm Jane Waite, and I'm chairing the seminar today. And it's wonderful that we're halfway through. So we're on to the sixth seminar in our this series on teaching programming with or without the use of AI. And we're focusing on how we can teach programming in schools where we're using machine learning and AI to support that kind of experience. And I have to say, I'm really excited because we've got Veronica here, who is one of the research scientists at the foundation. I absolutely love this research that she's going to present to you. It's filling an enormous gap in the field. So Veronica works with us at the Raspberry Pi Computing Education Research Centre, and she's looking at how students learn and engage with digital technologies. She's got a background as a computer scientist, and she's worked as a software developer and a technical leader, and her PhD is in learning analytics, where she explored using data to track students' creative processes with physical computing kits. So today, Veronica is going to be presenting her research on how large language model generated explanations are viewed by expert educators. And there might even be some of those educators in the room here, but of course, we're going to keep them anonymous. And she's going to be sharing some of the insights from the interviews and contextualize these findings within this theory, which I absolutely love, called feedback literacy. And I think it's going to be really important for us as we move forward in terms of LLMs. So without any further ado, so proud, Veronica, over to you.
Hello, everyone, and thank you for making the time to attend the seminar. I'm personally very excited to be here as a Raspberry Pi Foundation in-house researcher. This is a big deal for me to make it as a presenter in one of these seminar series, and I'm very proud and humbled to be here. As Jane said, I'll be presenting the findings from our short exploratory research study on using feedback literacy theory to explore expert educators' views of using large language model explanations of programming error messages in the classroom. But what do we mean when we use the terms large language models and programming error messages? In the context of this study, we used Cambridge University Press's definition of a large language model as a complex mathematical representation of language that is based on very large amounts of data and allows computers to produce language that seems similar to what a human might say. And by programming error messages, we mean those diagnostic messages generated by the compilers or interpreters when the code violates the specifications of the programming language. And I will be using those two terms a lot throughout this presentation, so apologies in advance if you end up dreaming about large language models or programming error messages tonight. And definitions out of the way, let's set the context for this research study. Programming error messages are notoriously difficult to decipher due to poor readability, including poor vocabulary, lack of sentence structure, and use of jargon. And programming error messages can often be a barrier in students learning to program, especially for novices who get stuck on errors they are unable to fix. Therefore, there have been ongoing efforts to improve programming error messages. And there is a whole research area dedicated to identifying and evaluating ways of improving and enhancing programming error messages. And using large language models to enhance programming error messages has been identified as a promising use case for using these AI models to support learning to program. And initial studies and initial research evaluating large language model enhanced programming error messages show that these models can potentially generate enhanced programming error messages that are novice friendly and potentially more easy to interpret and action than the original programming error messages. However, there is conflicting evidence on what makes an effective error message for novices. And there are many challenges like identifying the underlying misconceptions that cause the students to make the error in the first place, all the way to designing programming error messages in a way that actually scaffolds learning. So the question of what is an effective error message, programming error message, is still being answered with no conclusive evidence. And if we don't know what makes an effective programming error message, then how can we employ large language models to enhance them? And finally, there is a resounding lack of teachers' voices and emerging research to date of ways of integrating large language models into the classroom more generally. So we set out to make a small contribution towards filling that gap and reached out to educators to see what they think of using large language models for explaining error messages and what might that mean for them practically in the classroom. So we asked 2 research questions. First, what are secondary educators' views on the potential classroom use of large language model program error message explanations? And second, in what ways can a feedback literacy perspective support the analysis of these educators' views of potential classroom use of large language model program error message explanations? The study was made possible by having access to a prototype built by the Raspberry Pi Foundation digital team. The Raspberry Pi Foundation already have a Python code editor, or IDE, publicly available to anyone for free. And it was this IDE that was adapted to include large language model explanations. And the prototype was only available for this study temporarily, and it worked exactly the same as the currently available IDE, with the addition of the little question mark that you can see in the background next to the standard programming error message students normally get when they make an error. And when you clicked on this question mark, a large language model explanation of the original error message was displayed in a pop-up window. The prototype called the OpenAI GPT 3.5 API to generate the explanations. And the prompt was very simple. You're a teacher talking to a 12-year-old child, explain the error in the following Python code, and the original error message and the code would be supplied in the API call as well. And most of the large language model explanations were similar to this one, where the first paragraph included 1 or 2 sentences as an introductory preamble. Hello, looks like you've made an error. The next paragraph was normally a short explanation of why the error occurred. For example, you've made a typo. Next, a paragraph including an explanation of how to fix the error, something like you need to convert. And it always included the corrected code or a potential code solution towards the end of the explanation, despite the model not being explicitly prompted to do so. To conduct the study, we interviewed 8 expert computing educators. The interviews were semi-structured, activity-based interviews, where the educators got to experiment hands-on with the prototype, whilst completing an already existing Key Stage 3 Python programming task designed available on the Raspberry Pi website. And the task involved the generation of a random number, simulating a dice. The educators were encouraged to make the type of errors they typically see their students making, or errors they might be curious to see the output of the large language model for. And they were also presented with a set of selected examples of large language model explanations for consistency purposes across all educators. And they were asked questions about what they liked or disliked about the explanations they were seeing, how they thought these might help or hinder their students in the classroom, and what they considered to be good or bad about the explanation and why. We also asked educators about the broader benefits and challenges they perceive around using these explanations in the classrooms. And using a qualitative inductive deductive data analysis approach, we identified the main themes in the educators' answers and eventually correlated these to both enhanced programming error message design guidelines and feedback literacy theory. And we'll go into more detail about these 2 correlations in the next few slides. But first, more on the themes that emerged from the educators' interview answers. 15 themes emerged, which we separated in 5 reporting groups. Related to the content, the actual content of the explanations, the educators noted how the explanations always included a possible code solution, despite the model not being explicitly prompted to do so. And the educators debated the benefits and risks of that. The educators overall preferred that this code solution is either removed or delayed, rather than immediately shown to students, to deter from copying and pasting without thinking or understanding. And also related to the content of the explanations, the educators discussed the use of key concept words. And the educators wanted the explanation to build on the key concepts they try and teach in their classroom or are required by exam specifications. So they wanted the explanations to contain those key words and vocabulary they try and get students to use and understand and get used to, that discipline-related language. But this was inconsistent in the large language model generated output. Sometimes the language was too simplistic, missing out on those keywords. Other times you used language that students wouldn't have understood at Key Stage 3 level. And other times the educators felt it was appropriate. There were also format and style aspects of the explanations that the educators talked about. For example, all educators noted how the tone and explanations was positive and encouraging, something they liked about the explanations. And around the validity of the explanations, all educators encountered at least one invalid explanation. And invalid explanations either consisted of made-up errors, so hallucinations, the explanation addressing an error that didn't actually exist in the code at all, suggesting a fix that would have, at best, made no difference to the code, or at worst, introduced an additional error. And another type of invalid explanations contained correct information, but didn't actually address the learning objective related to the error. So it was a valid solution, suggestion. So for example, the explanation would suggest initializing a variable before use when the error was bad input type error. So it's a valid suggestion, but it wouldn't have addressed the issue. So, and the educators raised the potential detrimental impacts of invalid explanations on student, including potential confusion, leading to misconceptions, increased frustration, or even decreased confidence in either themselves or the feedback that they receive. And in addition to the content, presentation, and validity of the explanations, educators also highlighted aspects related to the learning and teaching process. For example, how the effectiveness of the explanations will always depend on students' level and motivation, no matter how well they are designed. We first look at how these themes correlate to established enhanced programming error message design guidelines, an area of research that focuses on ways of enhancing programming error messages to help students understand and action them better. And we use the guidelines proposed by Brett Becker and many others, which consolidates a lot of the research done in this area in 10 design guidelines. And 10 of our themes actually correlated to the guidelines on showing solutions or hints, providing scaffolding for the user, increased readability, reduced cognitive load, using a positive tone, and providing context for the error. So I've already mentioned the positive tone, as well as, for example, the educators talking about the explanations being detailed and avoiding jargon, positively relating to the guideline of increased readability. And these 10 themes represent educators' comments mostly about the explanation's content, presentation, and validity. So about what's included in the explanation. And they highlight how the explanation follows or breaks the guidelines. And I won't dwell on the correlation to these enhanced programming errors message guidelines for too long. This is further broken down in the paper if you want to look at it in more detail. But importantly, only 10 out of the 15 themes correlated to these guidelines. And they were, for the most part, those themes related to content, presentation, and validity. On the other hand, the themes related to the teaching and learning process, we were less able to correlate. But when we looked at feedback literacy theory, we were able to correlate all 15 themes. And if we look at programming error messages as a form of feedback, which it is, we can use feedback theories to analyze and potentially improve them. But what is feedback literacy? Providing feedback, which includes explanations, is a social interaction. So the feedback effectiveness will depend on the teachers' and students' competencies of engaging with that feedback, as well as on the feedback type. So the role that feedback serves from a pedagogical perspective. So let's look at these three components: feedback types, teacher feedback literacy, and student feedback literacy in detail. McLean et al. Formalize 4 types of feedback in their study. First, a telling type feedback. So a unidirectional, correct information to be transmitted from experts to passive students. Next, there's a guiding. As students start to think about feedback as a two-way event in which the feedback acts as a pointer in the right direction for them to apply. Developing understanding, in which targeted teaching from the educator is used by the students for their own learning to build on or adjust what they already know. And opening up new perspectives. Educators presenting new perspectives that students use to make sense of information, open to interpretation and critique to inform their own views. So the type of feedback shapes the role educators and students in this social interaction. And alongside feedback types, from a student perspective, we have these capabilities and dispositions students need in order to use the feedback effectively. And these competencies are formalized by Carlos as students being able to appreciate feedback processes as a two-way event where they hold some responsibility, making judgments, so understanding what the feedback is in connection to their task, taking action, acting on that feedback in order to move on, and managing affects, so managing the feelings that come with either positive or negative feedback. And finally, from a teacher perspective, teacher feedback literacy concerns 3 dimensions, which relates to, first, the educator's capabilities to design feedback or manage feedback practices in a way that supports students practicing their feedback literacy skills. Second, the way in which educators relate to the student, so that relational dimension, to support them in exercising the feedback literacy skills. And thirdly, the pragmatic dimension, those pragmatic decisions educators make day in and day out between the ideal feedback experience and the pragmatic realities of every day. And part of that pragmatic dimension may be choosing an ID which offers large language model explanations versus one that doesn't, depending on how well it aligns with their learning objectives. So, according to feedback literacy, effective feedback processes entail well-designed feedback with a clear pedagogical purpose, as well as these competencies students and teachers need in order to make sense of the feedback and use it effectively. How does what educators had to say correlate to these aspects of feedback literacy theory? Let's look at feedback types first. We can see how each theme correlates either in an enabling or limiting way to each feedback type. So, for example, including a possible code solution could enable a telling type of feedback where the passive student gets told the correct code solution, and probably limits a guiding type of feedback where students may not take the time to understand the code solution presented to them or attempt to reach a solution by themselves. Similarly, invalid explanations that are either made up or unrelated to the error can hinder students from developing their own understanding of what is going wrong in the code. However, educators also saw an opportunity in discussing these invalid explanations with students and opening up new perspectives on how large language models work and why the explanation was incorrect, So there, students can take an active role in interpreting the feedback using their previous knowledge or seeking alternative sources to scrutinize that explanation that they know is invalid. So the same theme can correlate to different types of feedback in different ways, showing how feedback doesn't take a single role based solely on its design. It is a social interaction, so it will depend on the interpretation by students and teachers, which is where the student and teacher feedback literacy skills come in. If we correlate the themes to student feedback literacy dimensions, we can see how large language model explanations, again, either support or hinder the student feedback literacy development. One theme that speaks to all 4 dimensions was the educator's observation that the explanation's effectiveness will depend on students' level of knowledge and motivation. So the students' level of knowledge will impact their ability to make judgments and take action of the feedback, and their motivation will probably impact their ability to appreciate feedback processes and managing affect. Another example is how a possible code solution being included in the explanation risks inhibiting students from taking responsibility for developing their own understanding and potentially reducing their learner agency, affecting their capability to appreciate feedback processes. On the other hand, several educators did mention that a solution can offer students actionable information on why the code is broken, possibly helping students make a judgment on their error. However, the way in which this solution is provided to students that helps their understanding without reducing their agency needs further consideration. Should it be displayed at all, and in which case, when? Furthermore, a detailed explanation that avoids jargon can help students make judgments and more easily evaluate what feedback means in the context of their own code, in a way that is accessible for them to understand. Finally, something completely missing from the enhanced programming error message guidelines correlation are the themes we correlate to teacher feedback literacy. And a specific set of comments aligned with both the relational and pragmatic dimensions of teacher feedback literacy was that the student-educator interactions may be reduced as a consequence of using large language models in the classroom. Using large language model explanations could serve a time-saving function, so educators noting that it could save them time, should this materialize in practice. But contrarily, educators voiced concerns about the detrimental impact on their relationship building with students. So interacting less with students could limit their opportunities to provide formative assessment and connect with students, get to know them, as well as potentially negatively impact their own confidence and professional development. And finally, related to the design dimension, educators spoke about the need for professional development on how large language models work and how to use them in the classroom in order to be able to design ways for students to use these effectively. And this was highlighted by all educators as something that is currently missing, but is urgently needed. In conclusion, from correlating educators' views to feedback literacy theory, we found that educators prefer to either remove or delay the code solution from their explanation and utilize key concept words based on what they're teaching to guide and develop students' understanding rather than tell. Related to students' feedback literacy, detailed jargon-free explanations can help students make judgments about their feedback, but invalid explanations can hinder this process. Therefore, we need ways of managing such invalid instances. But for the most part, educators didn't talk about eradicating them altogether or the need for them to be eradicated altogether. They talked about ways of flagging them up or using them as counterexamples or simply having visibility of them to be able to address them with students. And finally, educators brought up the need for professional development for them to better understand the implications of using large language model explanations in the classroom. as well as designing the use of large language models in a way that accounts for those benefits that educators currently and students currently get from face-to-face interactions. For example, teachers having visibility of the way in which students use the explanations to make up for what they currently learn whilst helping students to debug, both about the students as well as their own feedback practices. And correlating educators' thoughts to enhance programming error message guidelines, we can see how the large language model explanations either follow or break these guidelines. Solely from a technical perspective, concerning mostly this content presentation and validity of the information contained in the explanation. But correlating the educators' views to feedback literacy theory, we can take a broader perspective on how large language models might not only shape the content of the explanations, but the whole social interaction around giving and receiving feedback. And we suggest that combining enhanced programming error message guidelines, which is this programming specific lens, with feedback literacy theory, a general education lens, to analyze educators' views, provides a more holistic approach to investigating the purpose and pedagogy of using large language model explanations in the classroom. And I gave examples of how different aspects of large language model explanations, as highlighted by the educators, either support or hinder the development of feedback literacy skills. Taking a feedback literacy perspective helps us consider how students and teachers interact with these explanations and this feedback generated by AI models, and can help us design feedback interactions that support the development of feedback literacy skills in order to make the most effective use of that well-designed feedback. So from combining these two perspectives of enhanced programming error messages guidelines and feedback literacy, we recommend that large language model content should be encouraging, detailed, jargon-free, to use keywords consistently, and be in line with learning objectives. And a solution code should not be included or delayed. We also recommend that IDE design should ensure that educators can see their students use large language models and enable users to manage invalid explanations, to flag them and be aware of them and help students manage them. And finally, to optimize programming teaching using large language models, professional development and student learning materials combining feedback literacy, programming error messages, and large language models should be researched, co-created with educators, and delivered. This study was just an initial exploration of educators' views of large language model explanations with a limited number of teachers. We didn't do any prompting experimentation, and we didn't investigate directly with students. Future studies would definitely benefit from an increased pool of educators and diverse pool of educators, exploring how different large language model prompts might better align to existing guidelines, as well as working directly with students to observe effects on learning. And in particular, we would like to further explore the requirement for professional development for teachers around the use of large language models to explain these programming error messages, as a way of enabling teachers' active involvement in shaping the ways in which these tools are introduced in the classroom. These are some of the references, including a reference to our paper, which will be published in the proceedings of the ITICSI conference this year. And we do have a website where all the research materials are available, including an author copy of the paper. Feel free to reach out to me with any questions or any observations on this research. That's all for me. Thank you. Thank you very much for hearing me out. And yes, we think feedback literacy is a useful perspective of thinking about feedback and explanations. But I am really, really curious to see what you think. And I've got these questions to help you guide the discussion later if they're helpful, in terms of whether it's a helpful concept for you at all in the first place, and in what ways, and also how it might be useful for your practice in your work or your research. Thank you very much.
So can we all give a virtual round of applause to Veronica? That was wonderful. It's a really, there's quite a lot of complex technical stuff in there, but you were really beautifully paced and explained things really clearly. So that was wonderful. And one of the things that I kind of want to give a shout out at this point in time as well is Veronica's going to be running some teacher professional development on all of this as part of a research study. So if any of you are interested in potentially getting involved, then email her. But we will be doing like a call to action. But it's always good if there are people in the room who go, oh, I'm kind of interested in something like that, to kind of pick you up along the way. Thank you very much, and have a lovely evening or morning or wherever you are.
Thank you.